Before we dive in, let's set something straight. What you're about to hear is purely for educational and informational purposes. We are not here to promote, encourage, or glorify the making or use of nuclear weapons. Instead, we're peeling back the curtain on one of the most powerful and dangerous technologies ever created by humankind. This is a story of science, war, politics, and survival. Imagine a single device with the power to level an entire city in seconds. A weapon so destructive that its shadow still looms over our world decades after its creation. That's the story of the nuclear bomb, and today we're uncovering how it came to be, how it works, and why it continues to shape the balance of global power. The last time the United States carried out a full-scale underground nuclear test was September 23, 1992, deep in the Nevada desert. The explosion never lit up the sky, but it rattled the earth beneath the feet of nearby residents. The ground shook with the force of an earthquake measuring between magnitude 4 and 5, a bone-chilling reminder that even tests performed hundreds of feet below the surface unleashed tremendous energy. Since that day, the U.S. has stopped live nuclear detonations, instead shifting to what are called subcritical experiments, tests that allow scientists to study nuclear materials without triggering a full-scale chain reaction. Even so, the American arsenal remains formidable. According to the U.S. Department of Defense, the nation maintains more than 3,700 nuclear warheads today, with thousands more retired but not yet dismantled. And that's just one country's stockpile. Globally, there are an estimated 12,000 nuclear warheads, with the US and Russia holding the vast majority. It's hard to wrap your head around those numbers, but what's even more haunting is how far this technology has come. If bombs created 80 years ago could destroy entire cities, how much more devastating might modern ones be? The story begins in the early 20th century, when scientists like Marie Curie and Henri Becquerel discovered that atoms, once thought to be the smallest, indivisible pieces of matter, contained enormous amounts of hidden energy. Their work revealed the strange, invisible force of radiation, a discovery that would change the world forever. In 1938, European scientists unlocked the secret of nuclear fission, the ability to split an atom and unleash the energy within. At first, it was a scientific breakthrough. But in the shadow of World War II, it quickly became a race for survival. In the United States, the government launched the Manhattan Project, a massive secret program involving some of the greatest scientific minds in history. In July 1945, the first nuclear test, known as Trinity, took place in the desert of New Mexico. The blast turned sand into glass, created a fireball brighter than the sun, and shook the very ground beneath observers' feet. Just weeks later, the United States dropped atomic bombs on Hiroshima and Nagasaki, killing more than 100,000 people and forcing Japan's surrender. The war ended, but a new era began, the nuclear age. The Soviet Union was quick to follow, developing its own bomb by 1949. Soon, other nations joined in, and the world entered a dangerous period known as the Cold War. Nuclear weapons weren't just bombs. They became symbols of power, bargaining chips and high-stakes diplomacy, and the backbone of military strategy. By the height of the Cold War, the US and the Soviet Union had built tens of thousands of warheads, enough to destroy the planet many times over. To prevent uncontrolled proliferation, leaders signed treaties like the Nuclear Non-Proliferation Treaty in 1968. Yet, despite these agreements, nations such as India, Pakistan, and North Korea eventually developed nuclear weapons of their own. The genie was out of the bottle and putting it back was impossible. But how exactly does one build such a devastating device? It all starts deep underground. Uranium ore is buried in the earth, often in remote and tightly secured locations. Mining uranium is no small task. Heavy drills bore into solid rock, blasting through layers of earth to reach uranium-rich deposits. Controlled explosions and powerful bulldozers are then used to extract the ore. To keep workers safe from harmful radiation, many machines are operated remotely, reducing direct human exposure. Once gathered, the ore is transported to a processing facility, where the real transformation begins. The uranium rock is crushed into fine powder and treated with chemicals to separate uranium from the rest of the material. This produces a concentrated substance known as yellowcake. At this stage it looks harmless, a dull yellow powder, but this is where the danger begins. Natural uranium mostly consists of uranium-238, which is useless for weapons. What bomb makers need is uranium-235, a rare isotope that makes up less than 1% of natural uranium. To separate the two, yellowcake is converted into a gas called uranium hexafluoride. This gas is then fed into massive centrifuges, high-speed spinning machines that sort the lighter U-235 atoms from the heavier U-238 atoms. Over time, the concentration of U-235 increases until it reaches weapons-grade purity, over 90%. At that point, uranium has crossed the threshold from raw mineral to bomb material. But raw material alone doesn't make a bomb. It takes precision engineering and advanced design to turn enriched uranium or plutonium into a functioning weapon. Inside a bomb, the core of enriched uranium is carefully shaped and surrounded by explosives. These explosives are arranged in a way that, when detonated, compress the uranium inward with incredible force, bringing it to a supercritical state. This compression triggers a chain reaction, splitting atoms apart at lightning speed and releasing unimaginable amounts of energy. To make sure the reaction starts exactly on cue, neutron initiators flood the core with neutrons at the perfect moment, guaranteeing the reaction doesn't sputter but instead races out of control. Every component, from the timing circuits to the detonators, has to work flawlessly. A single misfire could cause a dud, or worse, an accidental detonation. The United States has developed many types of nuclear weapons, including the B-61 bomb, designed for aircraft, and the W-88 warhead, carried on submarines. Each is a marvel of destructive engineering, designed not just to explode but to do so with terrifying precision. Before deployment, weapons officers follow strict protocols. Safety plugs, known as arming wires, are removed in a specific order. The bomb remains inert until the last possible moment, ensuring that it cannot detonate accidentally while still aboard the plane. Once released, the bomb begins a deadly sequence. Gravity pulls it toward the Earth as it switches from external to internal power, activating onboard sensors. These systems check altitude, speed, and trajectory, waiting for the exact conditions to trigger the firing sequence. Barometric sensors measure air pressure, detecting when the bomb has fallen to the correct height, typically around 1,900 feet above the target. At that point, radar altimeters confirm the bomb's precise distance from the ground. Only when both systems agree does the bomb move to the next stage, arming the firing mechanism. Then, within seconds, the final safety barriers drop away, and the weapon is primed for detonation. Inside, electric primers ignite powerful chemical explosives, compressing the uranium core and initiating the chain reaction. A blinding fireball forms, hotter than the surface of the sun, expanding outward in an instant. Within a fraction of a second, everything nearby is vaporized. The destructive radius is staggering. Near the center, devastation is total within a third of a square kilometer. Outward, shockwaves flatten buildings, ignite fires, and hurl debris for miles. Radiation bursts outward, burning skin, damaging organs, and poisoning survivors. The fallout drifts far beyond the blast zone, carried by wind, contaminating soil, water, and air. Its effects can last decades, causing cancer and genetic damage long after the fireball has faded. It's chilling to imagine, but this is why nuclear weapons are often described as humanity's deadliest invention. They don't just kill instantly, they leave scars on land, people, and history that may never fully heal. From the deserts of Nevada to the cities of Hiroshima and Nagasaki, from Cold War missile silos to modern-day stockpiles, nuclear weapons remain a sobering reminder of what humanity is capable of creating and of destroying. Even today, the question lingers: are these weapons meant to protect us, or do they simply hold the world hostage under the constant threat of annihilation? It's a question with no easy answer, but one thing is certain: the story of nuclear weapons is still being written, and it's a story that will shape the future of humanity for generations to come. Imagine a weapon so powerful that it can erase a city in seconds, leaving behind not just ruins but scars that last for generations. The world has seen this kind of destruction before, and even decades later, survivors speak of the psychological shock as if it happened yesterday. Families torn apart, communities reduced to ash, and nations left with the heavy responsibility of rebuilding from nothing. Nuclear weapons changed the course of human history, and their presence still lingers in the background of global politics like a dark shadow. Yet as terrifying as they are, not every weapon of modern warfare is about sheer destructive force. Some are designed for precision, for stealth, and for technological dominance that quietly tilts the balance of power without ever making headlines. And that is where the story of the F-35 Lightning II begins. This jet is not just another aircraft. It's the most ambitious and expensive weapons program in human history, with a price tag that has soared past $1.7 trillion. To put that into perspective, that's more than the GDP of many nations combined. But the F-35 is not merely a fighter jet. It's a flying supercomputer, a stealth reconnaissance machine, and a command center in the sky. It is engineered not just to fight wars but to dominate them. For allies, it's a symbol of cutting-edge technology. For adversaries, it's a constant reminder that they could be seen, tracked, and targeted without ever realizing it. The road to the F-35 started in the 1990s, when the U.S. military realized its fleet of aircraft was aging. The F-16 Fighting Falcon, the AV-8B Harrier, and the A-10 Thunderbolt II had served for decades, but technology was advancing and adversaries were modernizing. A new generation of aircraft was needed, one that could replace several platforms at once. This challenge gave birth to the Joint Strike Fighter program, a global competition that would ultimately reshape military aviation. In 2001, Lockheed Martin's X-35 prototype emerged victorious over Boeing's rival design. The mission was ambitious: create a single platform that could be adapted for the Air Force, Navy, Marine Corps, and even allied nations around the world. From this vision came three variants. The F-35A for the U.S. Air Force, built for conventional runways. The F-35B for the Marines, with the ability to take off on short runways and land vertically like a helicopter. And the F-35C for the Navy, built with larger wings and reinforced landing gear to survive the brutal impact of carrier landings. Each variant serves a different role, but all share one thing: stealth, speed, and adaptability. But turning this vision into reality wasn't easy. The F-35 program faced years of delays, soaring costs, and political controversies. The first flight took place in 2006, but it wasn't until the 2010s that production truly ramped up. Critics called it a boondoggle, a money pit that would never live up to the hype. Yet today, over 1,000 F-35s are flying across 17 countries, forming the backbone of Allied air power. Despite its rocky start, the Lightning II has proven itself in combat and continues to expand its influence across the globe. The key to its power begins with stealth. Unlike older jets with sharp angles and exposed weapons, the F-35 is carefully sculpted to scatter radar waves. Its smooth curves, angled surfaces, and internal weapon bays make it nearly invisible to radar. Its outer skin is coated with radar-absorbing material, essentially a high-tech paint that reduces its visibility to enemy detection systems. Even the tiniest detail matters. Engineers say that a flaw as small as 1 mm could compromise stealth, which is why every component is built with surgical precision. Inside, the F-35 is just as advanced. The jet is built from titanium, carbon fiber composites, and aluminum-lithium alloys. These materials keep it lightweight yet strong enough to withstand extreme forces and blistering heat. But the F-35 is not the product of one factory, it's a global collaboration. Over 1,800 suppliers across 11 countries provide parts, from fuselages in Texas to wings built in Italy and the UK. The engines, Pratt & Whitney's F-135, come from Connecticut, while advanced avionics and cockpit systems are supplied by Northrop Grumman. Each part makes a journey to Lockheed Martin's final assembly lines, where human technicians and robotic systems work together with the precision of a surgical team. Laser trackers measure every detail to fractions of a millimeter, ensuring nothing is left to chance. And then there's the brain of the jet. With over 8 million lines of code, the F-35 runs more software than any other aircraft in history. It constantly gathers and fuses data from radar, infrared sensors, satellites, and other aircraft, presenting everything in a single streamlined display. For the pilot, this transforms the chaos of battle into a clear, manageable picture. The F-35 doesn't just fly, it thinks, analyzes, and informs. Its distributed aperture system gives the pilot 360-degree awareness, even allowing them to see through the jet using their $400,000 helmet. This helmet is unlike anything else in aviation. It tracks eye movements, overlays vital information directly onto the visor, and even lets pilots target enemies just by looking at them. Of course, none of this works without raw power. At the heart of the F-35 lies the F-135 engine, a beast that generates 43,000 pounds of thrust. It can push the jet to speeds of Mach 1.6, roughly 1,200 miles per hour, while still giving the Marine Corps' F-35B the ability to hover and land vertically. Before any engine is approved, it undergoes brutal testing, heat stress trials, thrust vectoring simulations, and noise signature analysis to ensure it performs without compromising stealth. Only after passing this gauntlet is the jet cleared for runway taxi tests, and then finally, its first flight with a test pilot. Once operational, the F-35 enters service at its assigned base. Pilots spend countless hours in advanced simulators, mastering the jet before taking it into the skies. On missions, the F-35 is a true multi-role aircraft. It can strike enemy positions with precision bombs, dominate the skies in air-to-air combat, conduct electronic warfare and perform high-risk reconnaissance, all without being detected. And when multiple F-35s fly together, their ability to share data instantly gives them a swarm-like power, overwhelming enemy defenses before a single shot is fired. This raises the question, is the F-35 the future of warfare, or simply the world's most expensive experiment? Critics argue that its price tag is unsustainable, while supporters claim it is redefining what modern air power looks like. One thing is clear, the F-35 symbolizes a new era where data, precision, and stealth matter as much as bombs and missiles. When you compare it to nuclear weapons, the contrast is striking. Nuclear bombs represent raw, unstoppable destruction, the power to erase entire cities in an instant. The F-35, on the other hand, represents control, finesse, and the ability to dominate without being seen. Both embody human ingenuity, but both also remind us of the risks we create. Every leap in military technology alters the balance of power and changes the fate of nations. So, which do you see as the greater threat? The overwhelming, world-ending force of nuclear arms, or the invisible dominance of high-tech warfare like the F-35? These questions are not just about technology, they're about the future of security, peace, and the uneasy balance that keeps global conflict in check. If you found this deep dive into military technology fascinating, make sure to share your thoughts in the comments. Do you believe the F-35 will secure peace, or do you think it's another step toward a world permanently on edge? And if you want more in-depth looks at the hidden truths behind the machines that shape our world, don't forget to subscribe. This is just the beginning of exploring the technology that defines our past, present, and future.